back to the still unnamed no-budget educational program. In this week's episode, we'll be discussing chemical bonds, but not how chemical bonds fall apart. That was last week's episode. I can't write an intro for the life of me, so without further ado, we'll start with the easiest aspect of chemical bonding to understand, which is the octet rule. In chemistry, atoms bond so they can have full valence shells, which is the outermost electron shell. Atoms want to be stable, and having a full valence shell makes atoms stable. The octet rule is pretty simple. 8 valence electrons equals a full valence shell. Hydrogen and helium are the exceptions to this rule. They only need 2 valence electrons for a full outer shell. Atoms must either lose or gain electrons. Atoms will do whatever's easiest, which means it's easy to determine whether there will be a loss or gain of electrons. If an atom has 1 to 3 valence electrons, it will lose electrons. When this happens, the atom becomes a positively charged ion, because there are now more protons than electrons. Positively charged ions are called cations. If an atom has 5 to 7 valence electrons, it will gain electrons. When this happens, the atom becomes a negatively charged ion, because there are now more electrons than protons. Negatively charged ions are called anions. If an atom has 4 valence electrons, it can either become a cation or an anion, because gaining or losing electrons is equally easy. It just depends on what the atom is bonding with. Atoms that already have 8 valence electrons are called noble gases. Because they naturally have a full outer shell, they never become anions or cations and cannot bond with other atoms. The first kind of bonding we'll discuss is ionic bonding, if the title card wasn't any indication. Ionic bonds are formed between metals and nonmetals. In order to have full valence shells, the metal atom transfers electrons to the nonmetal. The metal becomes positively charged and the nonmetal becomes negatively charged. Ionic compounds have quite a few unique properties. First of all, since we pretty much already went over it and since it's literally in the name, ionic compounds are made of ions. Ionic compounds are also exclusively crystalline solids and have high melting and boiling points. Many are also soluble in water, but not soluble in nonpolar liquids. The last property, and probably the most important, is their ability to conduct electricity when melted. This is why ionic compounds are called electrolytes. Yeah, electrolytes, what plants crave and all that jazz. Electrolytes are necessary for your body to function. This is because your body, simply put, runs on electricity. Your brain outputs less electricity than is needed to power a light bulb, and this signal tells other parts of your body what to do. Your body also sends electric signals to your brain, so your brain can decide how to respond. You're basically a weak electrical circuit contained in a mech suit made of bone with armor made of flesh. Wonderful, right? And that weak circuit needs electrolytes to function, or you, die or something. I'm not a biologist. The next bonds we'll discuss are covalent bonds. Covalent bonds are formed when 2 nonmetals share valence electrons in order to have full valence shells. There are 2 types of covalent bonds, polar and nonpolar. These are determined by the compound's electronegativity, which is an atom's tendency to attract electrons. Compounds with an electronegativity between 0.0 and 0.3 are nonpolar covalent compounds. Compounds with an electronegativity between 0.3 and 1.7 are polar covalent compounds. Compounds that have an electronegativity between 1.7 and 3.3 are just ionic compounds, and we just talked about those, so they're not really important anymore. The properties of covalent compounds are pretty much the opposite of ionic compounds. Covalent compounds are formed of molecules. Since the atoms don't lose or gain electrons, they don't have charges. Covalent compounds can also be solids, liquids, or gases. We're really ignoring all other states of matter here, aren't we? Alright, then I guess we won't be getting into time crystals and Anyways, covalent compounds have low melting and boiling points, as well as being poor conductors. Many are also soluble in nonpolar liquids, but aren't soluble in water. As the name suggests, metallic bonds are formed between metals. Neat, right? Metallic bonds are formed by the attraction of positive metal ions and a sea of floating electrons. Similar to ionic compounds, metallic compounds are very good conductors. However, unlike ionic compounds, this is because electricity and heat very easily move through the sea of floating electrons. Metallic compounds are malleable, which means they can be beaten into different shapes. They're also ductile, which means that they can be drawn, pulled, or extruded to form wire. Due to their electron-C, metallic bonds have a property called luster. This is caused by light being absorbed and re-emitted by the aforementioned electron-C. In layman's terms, metal shiny. The electrons in the electron-C are shared by all of the surrounding atoms, and finally, metallic bonds become stronger as you go from left to right across the periodic table. Wow, that was a lot, right? Man, I sure hope there isn't any more to discuss. Son of a... Naming compounds and calculating formulas is, thankfully, pretty simple. We'll start off with naming ionic compounds. If you somehow already forgot, I get it, I wouldn't be paying attention either. Ionic compounds are formed by metals into nonmetals. When naming ionic compounds, the first thing you do is you take the name of the metal. You leave that alone. Then you take the name of the nonmetal, you cut the end of it off and add "ide" onto it. For example, you take sodium and chlorine. Put them together, you get sodium chloride. Now, this is a little different when you use transition metals. Yeah, metals can transition, good for them, right? Most transition metals can have multiple different charges. For example, iron can have a positive 2 charge or a positive 3 charge. So when you mix iron and chlorine, the iron would have to have a positive 2 charge. So when you name it, it'd be iron 2 chloride, with the 2 being written as Roman numerals. This represents the atom's charge. Calculating the formulas for ionic compounds is even easier. First, you write the chemical symbol for the metal. Then you write its charge. Then you do the same thing for the nonmetal. Then, if they have a different number of charges, you switch the numbers around. So, for example, iron 2 chloride would be Fe2 plus and Cl1 minus. Switch those around, you get FeCl2, 1 iron, 2 chlorine. When the two atoms have the same number of charges, you just write the chemical symbols next to each other. For example, sodium chloride would just be NaCl, because sodium has a positive 1 charge and chlorine has a negative 1 charge. They just cancel out. Naming covalent compounds has a few more steps. We'll use 2 hydrogens and 1 oxygen for our example. That's water if you don't already know that. First, you take the element with the lower electronegativity. In this instance, it'd be hydrogen. You write its full chemical name and leave it for now. We'll come back to it later. Then you take the other element and change the ending to "ide," like you would do for ionic compounds. Finally, you add prefixes to the beginning of each element, which are dependent on their quantities. Since we have 2 hydrogens, we'd add "di" to the beginning of it. And since we have 1 oxygen, we'd add "mono" to the beginning of that. The final compound we would have is dihydrogen monoxide. So now you know the technical term for water and your friends can punch you in the face for being facetious. For another example of naming covalent compounds, let's take a single sulfur and 6-fluorine. Sulfur has the lower electronegativity, so it goes first. Then you replace the end of fluorine with "ide" to get fluoride. Since there is only a single sulfur at the beginning, we don't add any prefix to it. But since we have 6 fluorines, we do add a prefix to that. Our final compound should be called sulfur hexafluoride. Calculating covalent compounds is really annoying to write into the script because it's way easier to explain with pictures. So calculating covalent formulas, really hard for me to explain verbally, so just ignore that. I'm gonna use pictures because that's easier. So you start with the more electronegative atom. In this case, it's oxygen. We're using water as an example, by the way. It has 6 valence electrons. It needs 2 to have a full valence shell. Then we take a hydrogen. It has 1 valence electron, so we make them share electrons. This has 2. This has a full valence shell, but this has 7, so it still needs another valence electron. So we take another hydrogen and then bond it. So we have 2 hydrogen and 1 oxygen. They all have full valence shells. So we get H2O, because the less electronegative goes first in the thing. And there are 2 of them, so there's that, and then there's 1 oxygen. That's an O. I suck at writing with one hand when I'm looking through a phone screen. let's do another example because there's other stuff we need to do. Let's do carbon and oxygen, so like the stuff you breathe out. You start with the more electronegative element, so we have carbon, and then that has 4 valence electrons. So we need 4 more. So we take an oxygen, which has 6. We do bonds and stuff, so we get rid of those. We have to do double bonds here for reasons, but that still doesn't have a full thing. So we do another oxygen. And we just cross those out and more bonds. So the actually well-written one would be that. Each of these lines is 2 electrons. So this has 8, so 1, 2, 3, 4, 5, 6, 7, 8. This carbon also has 8, 2, 4, 6, 8. You know, it's science. Yeah, I forgot to write the thing for this, since we start with the carbon, and then there are 2 oxygen, CO2. There's a rule I also forgot to say. It's been a while, man. Carbon always goes in the middle, even though it's less electronegative than oxygen. That's why it's first here. I hope that makes some semblance of sense. I am not a professional. So, yeah, that's it. That's all. You know more about chemistry. Congratulations. Next time we'll be doing real science and testing if jet fuel can really melt steel beams.